Yes, hello everyone. My name is Omar Marzouk, and I've been working in the HPC team in Brightskies, Egypt for the past year, primarily on the DAOS project, focusing on exploiting the DAOS object-based storage for optimizing the storage and retrieval of seismic data, as well as using it for the retrieval and storage of data for AI workloads. The topic I'll be presenting today is the leveraging of DAOs for seismic data storage. But before we can go into details regarding our application, we need to add some context regarding seismic data, how it's collected, processed, and the formats it can be stored in. Seismic data is collected through surveys on large areas of land and sea, where, as we can see here, marine data acquisition is performed by a surveyor vessel or ship, which introduces a source of shock waves underwater that are later reflected by the different underlying earth layers at different angles and varying times. The reflected waves are then collected by hydrophones or receivers, and each of these waves represents a trace of data, which is the fundamental building block of seismic data. Each blast from the source represents a shot and produces thousands of data samples. This is why an area of 1,200 square kilometers can produce around 280 terabytes of raw seismic data, or even petabytes for larger survey areas. Once this huge amount of data is collected, it can be operated on by filtering, sorting, and otherwise processing it to generate a model of the Earth layers seen below. But before this data is processed, it needs to be stored in a unified and readable format. And while there are several data formats in the oil and gas field, the one most commonly used and the one we'll be focusing on is the Seg-Y format. The Seg-Y format is a fairly simple one. It stores some metadata and information regarding the file in the form of text and binary headers of fixed size, as well as optional extended text headers of variable size. But the part we're most concerned about is what follows the file headers, which is the array of trace data containing all of the information collected during the data acquisition process, and trace metadata describing the traces themselves. And it is this combination of metadata and data that is of crucial importance during the processing of seismic data. The metadata describing each trace, also known as trace headers, consists of 80 or more keys. Header keys include important data for each trace, such as shot ID, which is generally labeled as FLDR, source and receiver coordinates, and the number of samples in the traces data array. These keys are important because almost all of the seismic processing operations performed, like sorting and filtering, operate on these header keys, first to decide the access pattern of the data. Followed by the metadata is the trace data itself that was recorded by the receivers in the field. The data and metadata are stored in an interleaving structure until the end of the file, representing a bottleneck during the accessing of the data, as you have to pass over all the trace headers and data arrays to reach a specific trace. It is this Seg-Y format that is used in most seismic processing applications. However, this format offers some limitations when it comes to reading and processing this data. First of all, data is copied redundantly for each operation with each processing step. Also, a serial read of the entire file is needed for almost all of the operations, which offers significant overhead, like we just discussed. And for trace data to be read, its corresponding trace headers first need to be processed to determine the access pattern of the data arrays. These are all examples of obstacles we need to overcome using our DAOS-based solution. That is why a major target was to use the native DAOS object-based storage system to introduce a layer of separation between the traces headers, which are the metadata, and the trace data. Other potential goals are the use of the DAOS snapshot feature to reduce duplication, and the DAOS versioning object storage, through which we can minimize the amount of data we need to store. This is where our Seismic API steps in, which we like to call the DAOS-SEISMIC graph, or the DSG. Based on a typical graph structure, the DSG is built on top of the DAOS API and uses regular DFS routines to create, open, and close its underlying objects. Each graph can be accessed through its root object, whose interface allows the user to access many of the other customized seismic objects implemented in our graph. To better understand how this graph structure works, we need to take a deeper look. In this graph, we can see how we have managed to overcome many of the obstacles we mentioned earlier. As we can see here, the traces headers and traces data are separated into two distinct objects that can be accessed independently. In the middle region here, this highlights our indexing part, which allows us to theoretically group traces together by an arbitrary header key value and gives us direct access to their data, while practically no copies of the data have been made, no matter how many indexes we choose to construct. These groupings of traces are called gathers and are accessed through customized gather objects, and they can be formed to index the data on one key, multiple keys, or even custom keys. Once a gather object representing the data indexing using a specific header key has been created, any further access of data through this gather object is a direct one. No sequential reading of the data is needed. This enables us to access a wide range of metadata and useful information in a direct manner, just by accessing the needed seismic gather object. For example, we can directly access traces having a specific FLDR or shot ID just by opening the FLDR seismic gather object, which guides us to the traces we need in the graph, as well as gives us useful metadata related to the FLDR header key itself, like the number of unique FLDR values or shot IDs. Finally, the left part here holds many of the graph properties, like the number of traces stored in the graph, the headers normally found at the beginning of a Seg-Y file, and some other useful metadata. We can look at this graph as our own native seismic data format. And based on this format, we have developed our DAOS-SEIS API. Taking a quick look at our API, it supports the conversion from several other formats to the DSG format we just discussed, upon which we can perform any of the operations like fetching specific trace headers, computing the range of values for each header key, and most importantly, sorting and or filtering, which we like to call window the data. These are all operations that are supported by many other seismic processing frameworks, but our goal was to build upon, optimize, and extend these functionalities. What sets our API apart from the others is the build index functionality, which can be used to optimize and perform most of the other operations efficiently. So to benchmark and assess our DSG solution, we have compared it to SEISMIC Unix. SEISMIC Unix is an open source seismic package that offers most of our functionalities, and we have benchmarked our performance against them on Seg-Y files of sizes 100 gigabytes, 1 terabyte, and 10 terabytes. In this table, we can see the distribution of the number of traces, as well as the distribution of some important header keys, like the FLDR and CDP, which corresponds to the common midpoint between the source and the receiver. Our benchmarks were run on the Linux cluster provided by Lenovo, where our DSG API tests ran in a DAOS environment with 4 storage nodes and 1 computational node, while SEISMIC Unix ran in a GPFS environment of identical specification. The 3 main operations we addressed during our benchmarks were the parsing of Seg-Y files, the reading of traces filtered by metadata or trace header keys, and sorting, or in the case of the DSG API, the building of an index. So in the next few slides, we will review each of the results. In this slide, we compare between the parsing function provided by SEISMIC Unix and our own parsing function. Whereas the DSG API parses traces in batches, the SU library reads each trace individually, greatly increasing the number of I/O operations and converts it to their own native SU file format. This gives our API a 3x speedup compared to its counterpart in all Seg-Y file sizes. Our second benchmark was the filtering of traces based on one header key unique value. For this test, we chose to filter by FLDR and read one shot of data. It is clear here that the DSG offers no performance cost as data size increases. And it's consistent due to the way the DSG uses the previously built indexes during fetching the data. As discussed before, building the FLDR index in our example has allowed our program to open the FLDR gather object, which maps and conveniently returns the traces in the graph having the required shot ID. The SEISMIC Unix library, however, gives a performance that obviously degrades linearly with the increase in the data sizes, since it passes over the whole file to filter the needed traces or data. So in order to assess the performance of the build indexing functionality, we compared it to our own parsing feature to highlight the relative speed of data access. Here we can see that since our parsing function is fairly sequential and deals with all the traces, headers, and data arrays, the time it takes to parse the data magnifies greatly as data increases. Whereas building a new gather object representing the indexes based on another header key, which is the CDP in this example, takes only a minimal fraction of the time the parsing takes to parse the same data, around 5%. This is due to the fact that during the build indexing operation, only the traces headers are read, which compose only 3% of the combined trace metadata and data size, hence the significant speedup. Here we can see that the building of indexes based on different header keys has also provided a fairly consistent retrieval time. As we can see here, even though FLDR and CDP have different distributions and different ranges, the retrieval time is almost equivalent. After replacing our traditional sorting functionality with a simple index building and switching from synchronous calls to the asynchronous DAOS API, we managed to overcome one of our major limitations from last year's release of our DAOS-SEISMIC graph. Back then, we suffered from a 4x slowdown compared to our SEISMIC Unix counterpart due to the fact that we had to read trace headers entirely and sequentially. This year's release, however, offers a significant improvement and a major speedup in our sorting of header keys. Now, instead of actively sorting headers, we simply only need to build an index for the requested header keys to be sorted and perform a simple retrieval of data. Also, now that trace headers and trace data are separated in two different objects, the retrieval of headers is now much more optimized and independent from that of trace data. While we have achieved great improvements already, we still believe there is room for improvement. There are still a handful of bottlenecks that can be optimized in our DSG API. We also need to study the effect of parallelizing some of our functionality, which could give us an even bigger boost. Integrating our code with existing SEISMIC processing applications will definitely give us new ideas on optimization. And we plan to benchmark our API against even more optimized SEISMIC I/O libraries. Also, we are thinking of adding native support for compression, since that is also one more thing we can improve in our leveraging of the DAOS storage system to further reduce the I/O required while storing and retrieving SEISMIC data in our native DSG formats. So here we have attached links to our open source GitHub repo that contains some of our work, as well as a documentation for our DAOS-SEIS mapping for those interested in reading more about it. We would also like to extend our thanks to the Intel and Lenovo teams for their continuous support. And thank you all for listening. Please let me know if you have any questions.